Well, hello, my Theosophical Society buddies. This is Jeff Curtis coming to you from the Sierra Foothills again. And Happy New Year. I'm glad we have a chance to do this together. Uh, 2026 been interesting so far. Lots to observe, and think about, react to, that we care about and study here at the Theosophical Lodge and elsewhere. Um, the idea of the void, as in sunyata or emptiness, it rhymes. It's not, as you'll see, it's not directly related to scientific and cosmological type ideas, but there's an interesting correspondence that I think is worth exploring, and hopefully I'll have time to get there towards the end. So I'm going to do a little bit of a review here and things that we spoke about last time. Because I'm away from home and I don't have my figures with me from the time before, I'm just going to ask you to remember one of the plots that we talked about and dealt with that had to do with the Hubble observations, from which we got the notion of an expanding universe. The fact that the universe, it seems that the farther out we looked into the cosmos and measured properties we could measure, like the redshift, about distant galaxies, we came up with a relationship that would say that the speed at which they're receding from us, if we put that on a y-axis, um, and their distance away from us on the x-axis was forming a line that came in. There was like a linear relationship, this recession velocity of galaxies. Farther away from us, the faster they seem to be going and receding. And that allowed us to contemplate a back extrapolation. In other words, what if all the distances, what if the recession velocity is zero and things are maximally close together? What it implies is if you have a spherically expanding universe of galaxies and stuff, and farther away, the more it's expanding, that logically extrapolates back to an initial condition where all that stuff is located in the same place. And that birthed the idea of the Big Bang. Now, it was a very controversial idea, the Big Bang, when it was proposed. And there was many years when there was a big fight happening in the community of astrophysics. Do we believe this? Or maybe it's not really true. There's a steady state hypothesis that was popularized by a very famous and important astronomer named Fred Hoyle. That began to die away because over the course of the 60s, 70s, and 80s, the observational evidence using different so-called standard candles. Remember, we spoke last time about standard candles in cosmology, and this is identifiable phenomena which at a distance we know how bright they have to be on an absolute sense because they're well characterized and recognizable. And we know how bright they are absolutely because we've observed them in our own galaxy up close. We measure how bright they are way far off. We can then compare their so-called absolute brightness with their apparent brightness. And we can do that with a multitude of different objects. And that allows us to construct what are called distance ladders. Well, one of the distance ladders comes from an object called a type 1a supernova. That's a special kind of a recurring supernova event where you've got a white dwarf star circling a larger diffuse normal star of modest to very large size. And this white dwarf star goes around, it strips material off of the larger, more diffuse companion, and periodically that material accretes around the white dwarf, which is a very small, hot, dense star, accretes around that, hits critical mass, and undergoes a runaway fusion event that causes it to become very bright for a while. And it turns out they all behave about the same. When they go through this this brightening, where they've stripped material away from a host star, we know how bright that is. And so we can observe those in other galaxies and thereby refine our distance ladder out to the next scale of distances with high precision. And as in everything with science, when you figure out how to do something at the next level of precision and penetration, therefore, in terms of your mathematical analysis and models, something very interesting became apparent in the late 90s and has become even more apparent and complicated since then. But starting in the late 90s, we figured out that the very farthest away stuff that we could precisely measure was now falling off of the line that we used to have of recessional velocity versus distance. And what we were seeing was a slight upwards deviation, suggesting that the stuff that's really far away is accelerating, meaning that there's something more interesting going on than we thought. It's not like the universe is just expanding at a constant rate, it's speeding up at a level that is statistically significant. And then over a period of years, more and more data accumulated, and science is about statistically pulling signals out of messy, noisy data until you become certain that you know what you're looking at. So people are judicious and careful about announcing a discovery that big because they know it's going to attract lots of attention and therefore criticism. Well, it held up. And this then brought about a lot of deep thinking about the nature of the evolution of the universe and the nature of space and time. Because this observation resurrected an old idea originally proposed by Albert Einstein in the form of something that he called the cosmological constant. In terms of the equations of general relativity, it appears as a term lambda, capital Greek lambda. He proposed it way back when he was sketching out his theory of general relativity. Then it sort of fell out of favor. He abandoned it. He even called it a mistake. And people zeroed it out and forgot about it. Well, it came back because this accelerating nature of the expansion of the universe implied something about space-time. It implied that space-time itself has a certain inherent energy to it that is the thing that's driving an acceleration, because it takes energy to do the work of it. So that as space is being created, it seems to be being created faster and faster. And there is a net positive rate of change to the recessional velocity. That's a big deal. And what it means, or meant to astrophysicists at the time, is that there's a new constant of the universe. And we can go on, and we have gone on, to spend a lot of time thinking about the sources of that so-called vacuum energy, how it might arise, what it means at a microscopic level. But at a macro level, at a cosmological level, it means that space, time itself, has an energy density, which is what correlates with this positive cosmological constant. That energy density, it turns out to be 10 to the minus ninth joules per cubic meter. So a cubic meter, that's about the same as a cubic yard. 10 to the minus ninth joules is not much. It's a very tiny amount of energy that seems to be inherent in the nature of space-time itself. But it's way not nothing, and it's what's causing this acceleration in the expansion of everything we can observe. Uh, Now, interestingly, because especially since we have the James Webb Telescope and more refined observations since then, uh, we're able to look at what this rate of acceleration was at different distance scales away. It looks like it may not be entirely constant. There could be some warbles and warbles in it. That this cosmological constant may not be entirely constant. There could be a little bit more complexity to its history than was first appreciated back in the late 90s and early 2000s. That's an open question. We're going to be waiting for another few years of observational data before anything definitive can be said about that. But it's, that's just live. That's the bleeding edge of science, and we're going to be waiting to see what that answer comes up. Now, how do we think about this then? We can accept it as a constant of nature that, yeah, there's a vacuum energy and it's what's causing this newly observed phenomenon. But people like to go deeper. They want to think harder about it and contemplate if there's a mechanism, what's happening down at the Planck scale that might correlate with this. There's a bunch of ideas that have bubbled up, and a certain very large and kind of famous controversy. You'll recall, we've talked in here a few times before, back even over the course of years, when I've described something to you called the Heisenberg uncertainty principle. I want to now just remind you of what that looks like. And I've got it here in two forms. So the Heisenberg uncertainty principle, the top line says delta x times delta p will be greater than or equal to quantity h bar over 2, where h is Planck's constant. H bar is Planck's constant divided by 2 pi, to put it in terms of radians. And then the second 2 is there for reasons of the derivation that Heisenberg did. So delta x, that just means the uncertainty in position. Delta p means uncertainty in momentum. Momentum is just equal to mass times velocity, okay? You can recast this or rederive it using actually quite different math and assumptions and tricks, and you get to an alternative formulation, which you see on the bottom there. That says delta t, uncertainty in time, times delta E, which is a spread in energy or change in energy, is also greater than or equal to h bar over 2. How do we think about those two complementary relations? So physicists will pull one or the other out to use as they're applying it to certain kinds of experimental situations. Are we measuring energy differences and durations? Then you use the second one below. Are we looking at length scales, sizes of things, distances, and also able to measure velocities of moving objects? Then we use the first one. There's a little bit of a common theme and a common feel there to both of those equations. They've both been multiply verified in lots of experimental situations. I mean, like lots of experimental situations. So there's no exceptions to these. We find that these variables are complementary. The more you know about the location of something, the less you know about its velocity, and vice versa. the more you know about the energy change associated with some phenomenon, the less you know about its duration, and vice versa. Seems like there's something about the universe where if we, for example, pinch it down hard enough to get to small scales of spatial resolution, we're necessarily creating big amounts of momentum, which means motion, which means energy of motion. And so that's all they're related. If we're doing experiments that are probing the universe at very, very short durations, we seem to be encountering realms and phenomena with large energy changes, and large energies associated. Um, I'm saying this very loosely, but I hope the basic idea is coming through. Uh, Universe responds when we pinch it. And there's different ways we can pinch it, but two obvious ones. By the way, these are not the only two Heisenberg relations. We can come up with other ones in terms of rotational motions and magnetic states, currents and circuits and stuff. It's a broadly applicable idea, and it shows up in different manifestations. These are just sort of the two most famous and easily understood and employed. Well, this weirdness of this wiggliness, the universe not wanting to be pinned down, and our pinching it causing big responses depending on how we pinch it and according to which of these variables, uh, sort of opens up a realm of thinking that takes us down to phenomena at the Planck scale, because at the Planck scale is when we start encountering situations where the length scale is so small that the energy spread starts to look infinite, or big enough to create black holes. Reality really changes if you get down to the Planck scale, which is about 10 to the minus 35th meters. Very, very small. Um, uh, the nucleus of an atom is, I think it's about a femtometer across. Um, so that's 20, that's 10 to the minus 15th. So that's 20 orders of magnitude away to get down to the Planck scale. The Planck scale is unimaginably small, but it's still a real thing. What we figure out is that if we try to talk about distances much smaller than 10 to the minus 35th, the energy ranges and changes involved start looking infinite and too big to make any sense anymore. This opens up the idea of a quantum foam. I'll get back to that in just a second. So, where do people go with this? The idea of pinching the universe, chaos, weirdness, uh, tumult. Well, people first started to see evidences of strange things going on as we began doing higher and higher resolution spectroscopy in the 1930s. Our technology got good enough that we began to see deviations from the rules of quantum mechanics and spectroscopy as they had been derived in the late 20s and used to predict and understand the spectrum of hydrogen and other hydrogen-like atoms. That just means uh, atoms that have only, or ions that have only one electron circling a nucleus of some kind. So people began encountering deviations from theoretical expectations and realizing that, these deviations go away, or at least they become explicable if we postulate that the vacuum is not empty, and that strange things can bubble up out of the vacuum if we allow that they can do so for very brief periods of time. This includes things like electron-positron pairs or other types of particle-antiparticle pairs. A positron is just the antiparticle of an electron. So remember from relativity, E equals mc squared. You can say how much energy would it take to create an electron and a positron. They both have the same mass. It's a very, very small mass. It's about 1/2000th the mass of a single proton. But it's a finite amount of energy. You can use it to calculate how much energy would that be. Well, okay, is it possible to essentially have that much energy bubble up out of the vacuum, create things? He realized that it is possible that electron-positron pairs are briefly appearing in the space around the charges that he's studying quantum transitions of, thereby screening the Coulomb potential. So if you have an electron and a proton, you expect a certain amount of attractive potential. Well, if there's a bunch of electron-positron pairs very briefly appearing in the space between, those will segregate themselves a little bit so as to screen the Coulomb potential. That changes the observed energy levels of the hydrogen atom. And if your apparatus is good enough and your resolution is high enough, you can begin to pick that up and actually quantitate it. There were other such observations beginning to accumulate. So, for example, the anomalous magnetic moment of the electron was something that showed up and had to be explained also in terms of vacuum polarization. There was another spectroscopic effect observed at about this same time called the Lamb shift, which once again involved strange effects taking place between electrons and protons in atoms that caused slight deviations of spectral lines. But it's not the same as the U-Ling potential that I mentioned first. There was the observation of a strange force between conductors at short distances called the Casimir effect. This also could be explained in terms of heterogeneity in the vacuum, the idea that there's something happening in the vacuum. It's not a perfectly smooth, quiescent medium. It's getting actively involved in things when we do experiments of a certain nature that allow these vacuum gyrations, so-called vacuum fluctuations, to appear and manifest themselves. This was huge. It rocked the world at the beginning because people had long thought vacuum is a vacuum. It's empty of all matter. There's nothing going on in there. This is saying, well, you're just wrong about that. There's a lot going on in there depending on the time scale, the energy scale, the length scale that you're probing your systems at. This led to the development of two major paradigm shifts, major advances in our understanding of the universe. So here in my talks to the Theosophical Society, I've gone over the basics of quantum mechanics and interference effects and the fundamental basics of spectroscopy a few different times. Well, what happened since that? Because mostly when I'm doing that, I'm talking about between visible light and matter. Then that was generalized out into quantum field theory. Now, quantum field theory is even larger, more generalized, and really intimidating mathematically. I try to study it. It's right out there at the edge of my ability to really comprehend much and hang in with it. It's pretty advanced math. The idea behind quantum field theory is that the universe is permeated with different kinds of fields: an electron field, proton field, quark field, photon field. These fields are empty until you excite them or pinch them and bring about promotion to a higher quantum level in some region of space, and that represents then the appearance of an electron or a proton or a photon. And that it's such a powerful paradigm. There are many versions of quantum field theory. It's not some of the rules and phenomena and symmetries necessary to honor special relativity. So special relativity, you'll recall, is relativistic effects due to constant motion, not accelerated motion, but constant motion. Well, that can be done, and that's where quantum field theory comes from. So this has been developed and worked on, and the more it's worked on, even the more solid and plausible comes the idea of the vacuum being a very busy place. It's thrumming with energy and interactions, and it's why we now have the phrase and the concept, an assumption of this thing we call the quantum foam. That's foam, F-O-A-M, meaning it's like a foam-like interaction of thrumming, interacting fields and particles bouncing off of each other. You can almost hear it if you stop to think about it hard enough. It's a powerful and dazzling concept. And again, this would be what quantum field theory tells us reality is like when we get down to the scale of about 10 to the minus 35th meters in space-time that have certain kinds of symmetry rules applying to them and therefore defining the type of particle that they birth. There's a zero-point energy in all oscillators at the quantum level. So these fields, even when they are empty, they are still not completely without energy. Now it sounds like a crazy contradiction, and that's really the best I can do in English with my understanding of this quantum field theory suite of theories, actually. That idea, the violence of quantum fluctuations at the Planck scale, the existence of a pervasive zero-point energy associated with the ground state of the vacuum, or the ground state of all the quantum fields, starts to seem like that should mate up with the other kind of energy we were talking about earlier, the one that is driving the acceleration, the one I called the cosmological constant, lambda, the one that tells us there's 10 to the minus ninth joules of energy per cubic meter. Well, people have been working on that. And the best minds in quantum field theory now have quite long while realized that if you take the messages of quantum field theory seriously and do a best estimate for the amount of energy in the vacuum according to QFT, it should be about 120 orders of magnitude more than the astronomically observed vacuum energy that we think is what's causing the acceleration of the universe. That's a problem. So instead of 10 to the minus ninth joules per cubic meter quantum field theory, which predicts a lot of things very precisely and accurately. Quantum field theory says it should be more like 10 to the 111th power joules per cubic meter, which is an absolutely mind-boggling, frightening amount of energy. How could we not see that? How could there be 10 to the 111th joules of energy per cubic meter and we're not burned by it? Well, the explanations have to do with the fact that it's happening at small scales, and when you come up to macroscopic scales, it all smooths out, and that energy averages to something that's not burning us, because what we experience and what actually ends up being relevant to our macroscopic existence is energy changes. Where the energy set point is sort of another issue. But hey, that's just me, and but it's fun, I kind of like that. It means that scientists have a lot to do. People who care about this are not going to be getting bored anytime soon. It's an interesting and sort of humbling example of science trying to figure itself out and unify the quantum mechanical view of the universe with the relativistic view of the universe. Obviously, there's work to be done. Now, I'll kind of leave that off for a minute, and then I think I'll close a little bit on just saying a few things about, I'm not going to call it exactly a correspondence or a proof, but let's just call it a rhyme between the idea of a vacuum that actually has stuff in it and the void. Well, sunyata, the idea of void in Buddhism, we can use the word emptiness as one translation of sunyata. I found, as I was looking around and reading, I could find places where people were trying to really forge a link between quantum vacuum fluctuations and this near infinite amount of activity and stuff bubbling up out of nothing, and statements relating to the void and emptiness. It goes back to the great mind, one of the Albert Einsteins of Buddhism, Nagarjuna, from way back in the Buddhist period of India. I found myself over reading and thinking a little bit unconvinced. There was a little too much forcing of square pegs into round holes, as far as I was concerned. And I came out the other end of rereading and rethinking about some of this and realized that, it's just for me at least, I was having more resonance with the folks who would look at the idea of sunyata as something much more than emptiness. It's a way of looking at phenomena from the human point of view and stripping away dependent perception. Its absolute nature is unpredicable. We have no way to grasp the absolute nature because it's always going to be bigger than what we can see and measure and understand, because the causal chains of cause and effect leading up to that which we're perceiving and reacting to go all the way back to the beginning of the universe. They are effectively infinite, which means that our fullness to the vacuum. And to me, that was the closest I could come to putting these ideas side by side in a way that was at least some degree of symmetry and harmony to it. You can find much more than that if you go looking for it and trying to find people who are really working at uniting in a more explicit way quantum mechanics with Buddhist cosmology. I'm speaking here in my usage of sunyata is more of a guide to inner peace in terms of how we think about that which we perceive in deep meditation, and then hopefully someday, even as we're stuck in traffic, the emptiness of those phenomena and our responses to them. And a big element of that has to do with impermanence of these phenomena, that it's all arising, persisting, and dropping away. None of it's forever. Therefore, none of it is quite absolute, or the way people like to think of absolute. Okay, so that's as much as I have for tonight. I hope some of you at least found it interesting, and I'm wishing a lovely 2026 to all of you. All right, good night. Jeff, signing off.